Hello, I'm excited today to bring you a video on transforming functions. This is one of those topics a lot of people find very confusing, but I'm hopeful that when we start to identify some of the common features inside these transformations, that it will become a systematic approach for you that will be fail-safe. We're going to look today at this big, ugly function here that I have that actually is going to end up producing a graph that looks like this. But let's not try and get to the end game right away. We're going to go piece by piece, systematic, as I was saying. When I look at a function like this, in my eyes, I look for what parent function it stems from first, so that I know the family that I'm going to graph. This one has this cube up here that sticks out at me as being the identifier. Sometimes it's the absolute value symbol. Sometimes it's a square, meaning it belongs to quadratics. There's all sorts of different identifiers, but this one, the unique one, is cubed. So I know that this is going to belong to the cubic family. And so the graph that it's going to coincide to looks like this. And I always start with that, and I look for a couple points specifically on that graph. One of the points is the vertex. It's right at the origin here, 0, 0. That turning point right there is really important. The other point I look for is going to be at 1, 1. I also look at -1, -1. I look at 2, 8, and -2, -8. Now you're probably thinking, how did I come up with those? Well, I start with x values that are nice and small, like -2, -1, 0, 1, and 2. And then I apply the parent function to them, which in this case, remember the parent function is y equals x cubed. And so I stick each of those values, like -2, into x and get the corresponding y. So -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. And so I start with those points. -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. Start plotting those points. The next thing that I look at is applying stretches, compressions, and or flips. Stretches, compressions, and or flips happen from multipliers. This is a multiplier and this is a multiplier, meaning that the operation they're involved with is multiplying. Now each of those is going to have a separate but related role. Multipliers are related because they always stretch, compress, and or flip the graph. They are separate because one is a vertical transformation and one is a horizontal transformation. I can tell which is which by where they lie in the function. The 3 is outside the portion that is being cubed. Outside means that this is going to be a vertical transformation. Inside the part that's being cubed, inside the parent function, means that it is going to be a horizontal transformation. So inside means horizontal. So let's go ahead and apply those multipliers. The equation when I'm looking at just the multipliers is 3 times the cube of 1/2 x. So let's do that. The 3 out in front, I'm going to multiply all my y values of those points I just described by 3. And let's see that happen. Go up here. My multiplier is my a up in this big mess. And I'm going to change that to being 3. And watch this point right here. You'll see that output of 1 be stretched up to 3. Watch that happen. And almost there, and we are at 3. It's been stretched up to 3. Pretty cool. Now, this 1/2 inside is a little bit more confusing. What that essentially does is makes it so that our input values have to be twice as much as they were originally to get the same output, meaning that I have to actually multiply all my x's by 2 to get my same output. So where this input, my x value is 1, it's now going to have to be out at 2 to have that same output of 3. So let's watch that happen. I'm going to change my c value, that's what this is, I'm going to call it my c value, to be 0.5, and you're actually going to see the x's get doubled. It actually gets twice as wide. can't get that exact, so I'm going to have to type it in. There we are. So it has moved from 1, 3 to 2, 3. So you're actually going to multiply all your x's by the reciprocal of this value. So this is going to be multiplied by 2 over 1. All right. So far what we've done is we've multiplied our y's by 3 to stretch this up there, and then multiply our x's by 2 to stretch it out. So it's gotten taller and wider. The next thing we do is to perform any of our translations. That means shifts. I have a couple translations that happen in this function. I have the -1 and the +4. Translations happen by adding and subtracting things on our function. I'm going to go ahead and rewrite this with those translations, the shifts, put into the function. Now, once again, the -1 is happening inside, so that is going to be a horizontal translation or shift, and the +4 is happening outside the part that's cubed, so that is going to be a vertical translation or shift. Let's handle the vertical part first. It's a little bit easier to understand. That is going to increase all of the y values by 4. So my vertical one, that's going to be my k. I'm going to change that to be 4. And you see everything gets shifted up by 4. Everything goes up by 4. And I can't quite get that exactly, so I'm going to go ahead and type it in. 4. There we go. Everything got shifted up by 4. So the output that was at 2, 3 is now at 2, 7. 4 higher. 0, 0 has been moved up to 4. 0, 4. All right. Now, as I said, this part in the middle is a little bit tougher to understand. This subtraction actually delays my input values by 1. So I have to put in 1 more to get the same output. So that means it actually is going to move the whole graph to the right one. Everything happens 1 later. When it's subtraction inside, you move everything to the right one. Let's even write that down. For the horizontal part, subtraction causes it to move to the right. Addition will cause it to move to the left. This is subtraction, so it's going to move to the right. Everything happens 1 later. So let's go ahead. I'm going to change my h value to be -1, a -1. There we go. And we see the graph moving to the right 1. There we go. That has been moved. The translations moved it up 4 and to the right 1. And we have what I said we were going to end up with. I'll go ahead and turn on that original graph again, and we see it overlaps perfectly. There we are. We wound up with it. So once again, this is the process you should follow. Graph the parent function, in this case cubic, with those common starting points. Then apply your vertical and horizontal stretch compressions and or flips. Those will be your multipliers. Remember, outside means vertical, inside means horizontal. And the inside is going to be opposite of what you think. You actually multiply by the reciprocal of that multiplier. Then you put your translations in, your shifts in other words. And so this one is going to be inside the horizontal, moves to the right 1, subtraction means to the right, and then up 4. The outside is your vertical, it moves up 4. There you go, that's a transformation. We handled this big, ugly, huge function. Actually, I find it beautiful, but I'm a little bit geeky, so that's okay. I hope this helps you. You can use this no matter what the function is. You just have to identify what the parent function is, what the original shape of the graph is. Good luck, have fun.